Hello, I'm Mike McCulloch. So today I'd like to talk to you about Dirac's large numbers hypothesis. In 1937 he noticed several, you could say, coincidences that have been found by others and himself relating to things like, for example, the ratio between the electromagnetic force and the gravitational force as calculated for hydrogen atoms. If you take the electromagnetic force in that atom, and divide it by the gravitational force between the electron and the proton, and then you get a ratio of about 10 to the 40, which is a massively large number, as you can imagine. Also, it had been found by Edwin Hubble, or estimated by Edwin Hubble, that the size of the universe was something like 10 to the 26 meters. And it was well known that the size of the proton was something like 10 to the minus 15 meters. So if you put these together, you also get something like 10 to the 40. So there seemed to be some correspondence here between the gravitational force and the electromagnetic force, the ratio between them, and the ratio between the cosmic radius and the radius of the, you could say, the main particle, the proton. But it was even more interesting in that when people started calculating the mass of the universe and dividing it by the mass of the proton, they got 10 to the 80, which was interesting because it's obviously the 10 to the 40 squared. So what does this mean? Well, does this mean that mass is proportional to the radius or the distance squared? Would mass be proportional to area? Why would mass be proportional to area? That's very strange. Well, in quantized inertia, mass is proportional to area, because you can write a formula like this. And what this means is that the gravitational attraction in a particular volume, the gravitational acceleration between a particular volume, that's gm over r squared, must be equal to or greater than a number, which is 2c squared over theta, which is essential in the theory to make sure that the unreal waves seen by bodies, accelerating bodies, are not larger than the universe itself. So this comes from quantized inertia. And if you write this down and rearrange it, you get a formula like this. So the mass is 2c squared r squared over g theta, where theta is the size of the cosmos, g is a gravitational constant. And if you work out what 2c squared over g theta is, you get something that looks like pi. It's very close to pi. It's about 3.06. So mass seems to be pi times r squared. So mass seems to be something like area. So this might explain why in Dirac's large numbers the ratio of masses is the square of the ratio of distances. It might come from quantized inertia. So yeah, I think this means something. I think it's important. And I would recommend you you also look at a book by Alexander Unziger, who's often mentioning Dirac's large numbers, which is Einstein's Lost Key, published in 2014. It's a very good book, and I'd recommend that. So yes, I think this is an important issue and should be thought about a lot more than it is. So I hope you've enjoyed this short, and please do subscribe to my Patreon and become a member of my YouTube channel if you're interested in this kind of thing. And I look forward to seeing you next time. Goodbye.